Hi everybody, welcome back to Viral Integrals. So today we're going to be taking a look at this integral that evaluates to pi squared over 12. And we're going to be using the Basel result from a previous video, that is that the sum of the reciprocals of the squares is pi squared over 6. So we're going to be using that result. So let's get started. So before doing anything, let's just check that the integral is not hiding an endpoint problem. Near 0, natural log 1 plus x behaves like x, so the quotient approaches 1. At x equals 1, the value is just natural log 2, and the value should be positive. So first, to get started, we're going to put a parameter inside the logarithm and let it control the x term. This keeps x as the integration variable, while a gives us something to differentiate using the Leibniz Rule, which is exactly why this parameter choice is useful. The two parameter endpoints tell us what f, big F, is measuring. At a equals 0, the logarithm is natural log 1, so f of 0 is 0. At a equals 1, f of 1 is exactly the original integral I. Because the integration limits are fixed, the Leibniz rule lets us take a derivative of f of a directly by passing the derivative inside the integral, and then just taking the partial. The partial derivative with respect to a of natural log 1 plus ax is, using the chain rule and the rules for differentiating logarithms, you get x over 1 plus ax. And we will just note that 1 over x times that is just going to be 1 over 1 plus ax. So f prime of a is just that integral right there, the integral from 0 to 1 of 1 over 1 plus ax dx. And now we just evaluate that integral, and we find that f prime of a is equal to natural log 1 plus a over a. Now let's note that the limit as a approaches 0 of natural log 1 plus a over a is just 1. So f prime at 0 is just 1. And now we integrate f prime of a from 0 to 1 using the fundamental theorem of calculus. So f of 1, or big F of 1 minus big F of 0, is the integral from 0 to 1 of big F prime of a with respect to a. And f of 1 we know is I, and f of 0 is 0. So I is equal to the integral from 0 to 1 of natural log 1 plus a over a. And now let's pull out the common series representation for natural log of 1 plus x, or in this case 1 plus a, and it's equal to the following. Dividing both sides by a, and we get this. So natural log 1 plus a is equal to that series right there. And now we integrate that series from 0 to 1 term by term. The endpoint at a equals 1 is controlled by the convergent alternating series, and every term has become an ordinary power of a. For the nth term, the numerator has a to the n minus 1, and the denominator already has n. Integrating from 0 to 1 adds another factor of 1 over n, so the two denominators multiply into 1 over n squared. Putting those integrated terms together gives an alternating reciprocal square series. So the original integral is now the sum of 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared, and so on. So we'll use the Basel result from a previous video as the known full reciprocal square sum. We'll call that full sum S. So S is equal to pi squared over 6. And compare the alternating series to the odd and even pieces of S. We're going to split S into the terms with odd denominators and the terms with even denominators. The alternating series has exactly the same odd terms positive and exactly the same even terms negative. Every even denominator is 2 times some integer k. So each even square has a factor of 4. That means the even part is 1/4 of the full sum. Once the even part is 1/4 of s, the odd part is the rest of the full sum. Subtracting 1/4 of s from s leaves 3/4 of s on the odd denominators. The alternating reciprocal square series is odd terms minus even terms. In the notation here, that means a is equal to o minus e, because the odd denominators carry the plus signs and the even denominators carry the minus signs. Substitute the two pieces into a equals o minus e. 3/4 of s minus 1/4 of s leaves 1/2 of s. So the alternating square sum is exactly half the Basel sum. Now replace s with the Basel value pi squared over 6. Half of pi squared over 6 is pi squared over 12. So the alternating reciprocal square sum has the value pi squared over 12. Now we just return that value to the original integral. The parameter argument turned the integral into the alternating square sum a, and a is pi squared over 12. So the integral has the value pi squared over 12. All right, guys, I hope you enjoyed that, and we will see you next time.